In the last video, we derived the chord conductance equation, which tells us that the resting membrane potential is a weighted average of each ion's equilibrium potential. The only problem with that equation is that it quietly assumes that all ion concentrations stay constant. But that's not true. Ion channels are always leaking even at rest. Because of that, potassium constantly leaks out, while sodium constantly leaks in. So left alone, these leaks would slowly run down the gradients. Every ion's equilibrium potential would drift towards zero, and the resting potential would collapse. That means that something has to continuously push the ions back against their gradients. That something is the sodium-potassium pump. This pump is actively transporting ions against their concentration gradients, and because of that, it needs energy. That energy will come from ATP. Each cycle, it hydrolyzes 1 ATP to pump 3 sodium ions out and 2 potassium ions in. Now that we know the basics of it, let's look at some of its characteristics. Its first characteristic is ubiquity. Ubiquity means that every single cell has this pump, not just neurons. But why does every cell need it? Because many cells rely on the sodium gradient it creates to power other transports, such as pulling in nutrients, controlling the pH, regulating cell volume, and etc. These mechanisms are together called the secondary active transport. Another characteristic it has is electrogenesis, meaning it moves net charge across the membrane. If you look at the pump ratio, we can see that 3 positive charges leave while only 2 enter. That means that there is a net export of 1 positive charge every cycle. That directly makes the inside of the cell slightly more negative. But the pump's bigger contribution is indirect. By moving sodium out and potassium in, it maintains the very concentration gradients that set the equilibrium potentials of all ions. Turn the pump off and the potentials drift towards zero. The entire resting potential would collapse. So the pump shapes the membrane potential in 2 ways. Directly as a small, hyperpolarizing current from the 3-for-2 imbalance, and far more importantly, indirectly by maintaining the gradients that the chord conductance equation depends on. Besides being electrogenic, the pump has another key feature. It is dynamic. Its speed isn't fixed, rather it changes with demand. So that means that the pump speed depends on how much sodium is inside the cell and how much potassium is outside it. More of either speeds the pump up and less of either slows it down. You can see this during exercise. Every action potential lets a pulse of sodium into the muscle cell. That rising internal sodium is exactly what revs the pump up to restore the gradient before the next fire. One last characteristic is its energy cost. Running constantly isn't free. It alone can burn through a large share of a resting cell's ATP, sometimes even a third or more in neurons. One last note before we wrap up. We've mostly talked about sodium and potassium here. But chloride matters too. We saw it in last video's chord conductance equation. But sodium and potassium dominate, as their conductances swing the membrane potential the most. So that's why we ignored it in this video. To finish things off, if I had to put it all into one sentence, the resting potential isn't a passive accident, rather it's an active energy-consuming steady state, where leaks pull ions down their gradients, while the pump pushes them back up. It's 2 rates, locked in balance.